Okay, so on Monday we covered specification testing and the main principles behind specification testing. We saw that there were diffuse tests and focus tests. The diffuse tests have the null hypothesis of no spatial autocorrelation, but then the alternative is some kind of spatial autocorrelation, not a specific kind. In contrast, the focus tests have a very specific alternative and are formulated as tests on constraints on the coefficients, the constraint being the coefficient is 0, right? So there is no spatial model at all. And we saw that there were three, if you wish, classic principles that all derive from the maximum likelihood estimation paradigm. The one that you're most familiar with, an asymptotic t-test or a wall test, is basically a test on the coefficient, on the significance of the coefficient itself. Then a likelihood ratio test is a test on the difference in the objective function. We can call it fit, but it's not strictly fit. In the likelihood, the maximized likelihood between the unconstrained model and the constrained model. And again, if that difference in the likelihood is large enough, then we reject the null. And then the third principle is a little more esoteric and has to do with the score or the slope of the likelihood function. And again, we compare the slope at the unconstrained maximum, which is horizontal, it's a tangent, to the slope at the constrained point, which is the 0. And again, if this slope is large enough, then we reject the null hypothesis. And this last strategy of testing, specification testing, is actually very fortunate because it only requires estimation of the model under the null hypothesis. So estimation of the constrained model, constrained in the sense of having the spatial parameter set equal to 0. So in most instances, that is simply a standard linear regression that can be estimated by means of ordinary least squares. So that's the easiest possible of worlds, but this principle also extends to more complex models, and that's where it really pays off. For example, it's really complicated to estimate a spatial probit model. So if you can develop a specification test for spatial autocorrelation based on the residuals of a standard probit model, that's fantastic because then maybe you don't ever have to go the route of having to estimate that model. And similar, as we'll see in a couple of weeks, in the case of panel data models, you know, random effects panel data models, they're not the easiest to estimate. So especially not with spatial effects. And so if you can avoid that whole thing, then so much the better. So that's the attractiveness of these Lagrange multiplier or score tests, even though in terms of power, they don't necessarily have the greatest power. In fact, the likelihood ratio test of the three principles tends to have the greatest power, but by the same token, they're relatively easy to implement. Not as easy as in the traditional standard mainstream econometrics cases, where most Lagrange multiplier tests boil down to an auxiliary regression. Typically, some function of the residuals regressed on some variables as very easy to do. The test boils down to some form of adjusted R-square. That's not the case in the spatial domain. As we saw, the derivation of these Lagrange multiplier tests is actually kind of a pain because you need both the first order derivatives, you need the second order derivatives, you need to figure out what the information matrix looks like. So that's in the full spatial model, and then you set the parameter to 0, which simplifies the whole thing tremendously. And so last week we ended, or on Monday I should say, we ended up with a Lagrange multiplier test for with the error model as an alternative. which we saw was related to the Moran's eye, a scaled form of the Moran's eye, basically. And then we also saw the Lagrange multiplier test for a lag model, which is a lot more complicated. So what we're going to do today is kind of build on that a little bit, and first look at two additional forms of these Lagrange multiplier tests that fix a particularly difficult problem in practice, namely that both the Lagrange multiplier tests also have power against the other form of a spatial model. So an error test has power against the lag model, the lag test has power against the error model. So then they're kind of corrupted. And so these robust tests are not robust in the sense of, say, the white standard errors, which are heteroscedasticity robust, but they're robust in the sense that they are kind of, maybe they should be called filter tests, and that they adjust for the possibility that the other alternative might be present. And so we'll do that first. Then we'll talk a little bit about higher order tests and the pros and cons of and again, as it turns out, these higher order tests are not standard in terms of mainstream econometrics. The spatial domain brings something more complex to it. As I mentioned last time, Moran's eye is a very general principle, and you can extend it to other kinds of residuals. And so we'll look at the case of two-stage least squares residuals here, and then I'll give an illustration of a specification search. And I have a bunch of examples, and then I think I'll have enough time to walk you through that with GeoDa and GeoDa space. They're basically the same. Readings, the same thing. The respective sections in Anselin and Ray, and then the original derivation of the robust tests is in that 1996 article. Okay, so what are these robust tests? First, let's just recap, and I changed the notation a bit because, as you'll see in a minute, it gets very complicated. So this at least makes the notation somewhat tractable. So the Lagrange multiplier error test I have rewritten here as a ratio of d lambda squared over t, and d lambda is basically the numerator in the LM error test that we saw on Monday. So that's this cross product of the residuals with their spatial lags, the E prime WE, divided by basically E prime E divided by N, which is a consistent estimate for the error variance. And then T is our trace term, the trace of WW plus the trace of W prime W, right? The trace of W prime W is the sum of squared elements of the weights matrix. That's a generic matrix algebra result, but the WW does not have that simple expression. So even though these are formidable matrices, you know, the trace of W prime W is the trace of an n by n matrix. You actually never have to do this matrix multiplication. All you need to do is sum the squares of the weights in the weights matrix, and since the weights matrix is mostly zeros, that's not that many numbers. So that is very nicely scalable. WW is not that simple. And then the LM lag test is also made very simple here as d sub rho squared divided by capital D, and d sub rho squared is the counterpart of d sub lambda. So it's a cross product of the residuals with the spatially lag dependent variable in this case, again divided by the same E prime E over N term. And then D is this monster, which consists of two parts. One part is the T, the trace term that we had before. The other part is this sum of squared residuals, if you wish, from this auxiliary regression. So those are the pieces. And so the other tests I will express in terms of this notation. So d lambda, d rho, D is our trace term, and then capital D is this big thing that we see here. So what's the problem? As I mentioned, both these tests have power against the other alternative. And the formal derivation of this is in the paper, but the bottom line is the following. If you've done some econometrics, you may know what a non-central chi-square distribution is. So you can think of a non-central chi-square as a chi-square that's shifted a little bit out, right? So then if you do the significance on the true chi-square, you basically cut in the wrong part of the distribution. So your tests are biased, in other words. And this is what happens when the true null hypothesis holds. So you have no, let's say, spatial lag, but you do have spatial error autocorrelation. Then the LM lag test in that case. So think of a model with a rho for the lag and a lambda for the error term. So rho is 0, the null hypothesis is satisfied, but lambda is not 0. In that case, you can show with a lot of fancy algebra that the actual distribution of the test statistic, which should be chi-square with 1 degree of freedom, actually shifts and becomes non-central chi-square. So that's a problem, right? And the same holds for the other one. So if you, under the null, lambda is 0, but rho is not, then again, this test for lambda is not chi-square with 1 degree of freedom, but it shifts out a little bit. So the idea of the robust test, and I think it's, in hindsight, is not a good term. It should be, because people think of the wrong thing when you say robust. They think they're better than the other test. Well, no, they're not. In fact, we'll see that you actually have to be very careful in the interpretation. But they're filtered in the sense that, and when you see the test, you'll see what I mean. The effect of the other null hypothesis, so to speak, is taken out of the test. And literally, the value of the test goes down, right? So then the question is, how much down does it have to go? So you can think of this graphically as it should be a chi-square, but it's not. It becomes a non-central chi-square, so it shifted a little bit. So now we're going to adjust the test so that it shifts back and is indeed a chi-square with 1 degree of freedom. So that's, in a nutshell, what this very fancy derivation does. And here are the tests. So the robust test for the robust Lagrange multiplier test for spatial error autocorrelation is this ratio. So look at what is in there. On the top, in the numerator, we have the d lambda. That's the one that we had before. But we subtract something. We subtract this, basically, d rho divided by d. So that is basic. That's not quite the LM lag test, but the LM lag test is d rho squared divided by d plus t. So we divide by d and we multiply by t. It's very complicated how you get there, and I won't go into details, but it's a lot of, working with the second partial derivatives, so the information matrix. And then in the denominator, we also have a term. So it's no longer t as it was in the original test, but it's t multiplied by 1 minus td. And so, you can show that there's then, this transformation, if you wish, or the filtering kind of shifts the distribution back to a proper chi-square, right? And for the lag, it's even, it's actually more complicated, but written like this, it's simpler. It's the difference between the two statistics, the two numerators that we had, squared, and then divided by d minus t. So in the original test, it's d plus t. Here's d minus t. So then what does this do? This basically takes out the potentially corrupting effect of the other alternative and switches the test statistic back from being a non-central chi-square to being a central chi-square with 1 degree of freedom. And this is a very generic principle. It has been applied not just to spatial tests, but in fact the original application was in another domain. It was looking at how tests were affected by serial autocorrelation. And you can extend this notion, and we'll revisit this later, in a panel data setting. There are all kinds of different alternatives you could consider. You could consider random effects. You could consider serial time series autocorrelation. You could consider spatial autocorrelation. So you can derive a test for each of these separately, which is what we call marginal tests, or you could derive a test for each of these, correcting for the possible presence of these others. And these tests, if you run ahead and look at the material for panel data, these are extremely complicated, but it's the same idea. So if one of these other alternatives is present, then the actual distribution of the test statistic becomes non-central chi-square. So we want to shift that back so that our inference is proper. So this is all based on very sophisticated asymptotic reasonings. And one of the strange and maybe counterintuitive things about these tests, and that's why the terminology of robust tests may be a little misleading, is that you should not consider these unless you reject the null with one of the standard Lagrange multiplier tests. So oftentimes, and I've seen it, the reaction is, oh, the LM error test is not significant, but the robust LM error test is significant, so that has got to be better. Well, it isn't. If the LM test is not significant, stop. Don't even look at the other one, right? And that's a very peculiar phenomenon. It has to do with these, asymptotic properties with locally equivalent alternatives and things like that. So the bottom line is only use it when you reject the standard LM tests. And we'll see in a few minutes how we can use this in a model specification search strategy. So basically, by looking at the Lagrange multiplier statistics and then, as appropriate, looking at their robust forms, we can decide with quite a bit of reliability which is the proper alternative, which is the most likely alternative model. Now remember, always in a testing framework, especially in a classical statistical framework, you don't accept the alternative. You reject the null. And so rejecting the null is really the only thing you can say with a quantifiable uncertainty. That's your p-value. You reject the null with that p-value. But that doesn't mean that the alternative is the one you had in mind. That's always the problem in specification testing. So just to give you an example, this is a standard output that you would get in GeoDa. So we see Lagrange multiplier lag, 51, highly significant. Lagrange multiplier error, 53, highly significant, right? And then you see the robust forms, and you see how the robust forms really shrink. So we have corrected the effect of the other possible alternative out of there. So the lag one drops from 51 to basically 3, and the error one drops from 53 to 5. And so at a 0.05 significance level, the robust lag test is no longer significant, whereas the robust error test is. And so this is a case where you can use this to suggest that error is the most likely alternative, right? Now, in practice, it's not always that simple, and we'll see that in a few minutes, and I'll talk about that a little bit. So, but this is a kind of a classic illustration of the fact that these robust tests, and that's why I like to also call them filter tests, they really take the original value and take something out. And if after you do that, there's still enough left, then you have some confidence that you have the proper alternative. If you take out too much, then you have no longer any evidence of this particular alternative. So that's the first set of extensions of what we did on Monday. The second set of extensions deals with higher order alternatives. And so a higher order alternative would be a model that either contains both a lag and an error term, or it could be models that have multiple orders of these. And I won't dwell on that because that's hardly ever used, but you can think of a higher order spatial lag model which would have first order spatial lag, second order spatial lag, third order spatial lag, anything up to order p, say, and then the same thing for the autoregressive error model, anything up to the order q. So you have, just like in time series, you have ARIMA models with an AR part and an MA part with different orders. You can think of that here as well as possible alternatives. In the spatial domain, except from a few theoretical papers, I've never seen it used. So typically, a first order is good enough. Occasionally, you see a second order model, but never, I mean, at least I haven't seen any with any higher orders than that, except in theoretical papers that just kind of set out the framework. But this one is kind of useful in some sense. It's also kind of a potentially misleading test. So the null hypothesis is no spatial anything, right? No lag, no error, nothing, right? And the alternative is that both are present, okay? So when both are present, then again, it's the same thing. You set up the alternative model, you get the first order conditions, second order conditions, do all the derivations, plug in the zero values for lambda and rho, and then your score test falls out of that. And the result is this thing, which is a combination of the pieces that we already saw. So you see, you recognize the first part is the LM error test. The second part is not the LM lag test. Now, if you really paid attention, you would recognize this right away. Does this look familiar? The bottom. So the test for both is not the sum of the test for each, but it's the sum of the test for one plus the robust form of the other one, which is a non-standard result. So typically in econometrics, when you do a test for two forms of misspecification, let's say you would do serial autocorrelation and heteroscedasticity, then a test for both is the sum of each of the tests. For example, the Jarque-Berat test that we use for normality is really a test against two features of the distribution, the skewness and the kurtosis, the third and the fourth moment. And so this test has 2 degrees of freedom because it's the sum of two 1 degree of freedom tests. That's the usual case. But in this case, because the lag and the error model are so intertwined, this really comes from the fact that the matrix, the variance-covariance matrix, is not block diagonal. So these two tests do not sum up. And instead, it's a combination of one of them with the robust or filtered form of the other one. So that's a non-standard result. So as I said, the standard textbook case would be that the LM test for the two is the sum of the two marginal LM tests, but that's not the case. And just to show you that I'm not making this up, of course you could say, well, this is how you wrote the software, right? So, yes. But if you look at the results, you see the lag tests are 51.3 that we had before, plus 5. You add these two up together, and you get 56. And then if you do the other way around, the LM error test with the robust lag, which is the one we saw on the slide, you also get 56. So that's kind of a quirky thing. What does that mean in terms of the interpretation of the test? This is where you have to be very careful, because typically people can get all excited and say, oh, look, the SARMA alternative, the test for the SARMA alternative is highly significant, so it's got to be a higher order model. Well, not so fast, because look at what this consists of, right? This consists of two parts. And so if the first part is very, very significant, then it doesn't really matter what the second part is. It's going to stay very, very significant, and vice versa. So as we saw, there's two parts to this. One is either the LM error test or it's the LM lag test. If these are highly significant, the SARMA test will be highly significant as well. And that doesn't mean that it's necessarily a second order model. So I like to say, use this with caution. It can be useful if, say, the one directional tests are not really that significant, but then the two directional test is, but it's basically something that probably shouldn't even be reported, you know, in hindsight, because it's more confusing than anything else. And I mean, there is a part of spatial econometric practice out there that just loves these higher order models, and I like to keep things simple. So if you see indication that in fact you might need a higher order model, I would say go back to the drawing board, rethink your model specification, check out the weights that you use, and maybe by reformulating the model you end up with something that only has one spatial parameter. Spatial parameters are enough of a pain to deal with, not so much in terms of estimation, but in terms of interpretation. You know, you have these direct, indirect effects and all that stuff. So if you can somehow get rid of them by respecifying your model, so much the better, right? And in the same vein, if you think you have a higher order model, maybe you need to rethink what it is you're doing, because just write out the reduced form. And the reduced form will show you how you're basically mixing different things together, and so that the effect of the immediate neighbor is not just its coefficient, but it's also some combination with another coefficient. And so then, you know, maybe think of a way to redo the weights or redo the model formulation so that you can keep it simpler. Simpler models are always better. So that's the higher order alternative. And then we have the two-stage least squares case. So that's where we exploit the properties of Murray and Zai to extend them to models other than a standard regression case. And as I mentioned the other day, that no longer uses the framework of maximum likelihood, even though these tests, as we'll see, look a lot like Lagrange multiplier tests. In the strict sense, they are not, because they're not based on a maximum likelihood framework. So instead, they require explicit, you know, derivation on the basis of the proper central limit theorem. And so these are central limit theorems that allow for dependence and allow for a little bit of heterogeneity. So they're basically in the same spirit as the classic central limit theorems that you may be familiar with from the textbooks, but they're more complicated in that they allow for this weird edge effect in spatial dependence. If you remember when I talked about the asymptotics, if we have expanding domain asymptotics, we basically change the weight structure as we grow the sample, and that's an additional form of instability that we somehow have to take into account. This is all highly theoretical stuff. In practice, you don't care, you know, if it works, it works. Why it works, you know, at the end of the day, you don't really care that much. But the bottom line is if you want to do this and if you want to prove this, it's a lot more complicated than the classic case. And the one thing you cannot do is to assume that all the classic properties just kind of extend to the spatial case. They do not. For example, as I mentioned a couple of weeks ago, the maximum likelihood estimator, even though it was presented in a paper in 1975, it actually hadn't been proven to be consistent and have all the properties of a maximum likelihood estimator until about 10 years ago. Because it does require its own specialized machinery to get the proofs and the asymptotic results. But never mind, we can apply Moran's I to residuals of a two-stage least squares regression, and then we can get a kind of a generalized Moran's I expression. And the numerator is very easy. The denominator is where all the, you know, difficulty is. So the numerator is just the Moran's I in its usual expression squared, which is basically what we saw in the Lagrange multiplier test. The denominator is kind of a variance expression for that statistic, and that's the hard one. So the numerator is just what we always do. We just plug in two-stage least squares residuals instead of the ordinary least squares residuals, but for all other purposes, practical purposes, it's the exact same thing. So again, if we have row standardized weights, then this S sub 0 is n, and the two cancel out, the two n's. Here's our friend the variance. And you see this is a bit of a monster, right? And you have the trace, the same trace we had before, RT. We have the sum of all the weights squared over n. So if it's row standardized, that is actually n. So that is our capital T divided by n that we had before. And then the second term is just a pain in the neck. You know, it has spatially lagged variables in there, including the endogenous ones, that's Z. Z is all the variables. Q are the instruments. So all the instruments are here. And then, of course, the residuals are the E term. So this is a pain. But as it turns out, if there is no spatial lag in the model, so this variance derivation is perfectly general and applies to a model that has a spatially lag-dependent variable. That's where its original motivation came from. If you have a model with a spatially lag-dependent variable and you look at the residuals, is there still evidence of remaining autocorrelation? And ideally, there shouldn't be any, right? So how do you test for that? You can construct something that looks like a Moran's I, but has a different variance. And this variance is very complicated. However, if you don't have a spatial lag in there, then a lot of things simplify, as it turns out. And then we end up with this term, which is exactly, you know, looks exactly like a Lagrange multiplier test. It's not quite, it's scaled. There's an n term in there, but other than that, the other pieces are the familiar pieces. The cross product of the residuals with their spatial lags and the sum of squares of the residuals in the denominator. And then our friend, the trace term, is there again, right? So easy to do, easy to compute in the standard case, a little less easy to do in the case with the spatial lag. Okay, so now what do we do with all these things, right? And we do what is called a specification search, which, strictly speaking, you don't ever want to talk about because you're not supposed to do this because of our pre-testing problem, right? But this is a real issue, and there's a large literature dealing with this. So the principle is, how do you figure out what is a better model? You know, so you have a model, as I mentioned before, all the assumptions are about the error terms. We have the residuals. How can we figure out, by means of the residuals, that there's something wrong about the assumptions that we're making about the error terms, right? So we saw that each of these specification tests is basically has a distribution. We can get p-values and all that stuff, but that is in isolation. That's critical. It is in isolation, as if this is the only test you ever do in your life, right? Nobody does that. Everybody tries different models, looks at, you know, different specifications. In fact, you know, if you've been exposed to the machine learning world, you know, you never even worry about specification tests. You know, you just try one model after another and see, using cross-validation and other techniques like that, which one fits the best. You never even worry about this, right? But in econometrics, and to some extent in statistics, you do worry about it. And there's basically two ways to go about it. One is from simple to complex. The other one is from complex to simple. And simple to complex is called a forward strategy. So you start with a simple model, you do diagnostics, and then from the diagnostics, you figure out what might be a more complex model, and then so you keep going forward till you stop. Or the other approach is the other way around. You start with the most complicated model that you can think of, and then you start testing constraints on the coefficients. Constraints in the sense of setting them to 0. That's the sense of the constraint, right? And so that's working backwards. And there's huge discussions in the literature. Hendry is the main proponent of the backward strategy from complex to simple. That's all well and good in a standard regression situation. A lot of this literature comes from time series, like how many lags do I include? And so you start with as many lags as you can think of, and then you start testing, can I drop the 10th order lag, and can I drop the 9th order lag? And you keep shrinking the model, so to speak. That's where it comes from. In space, it's not that simple, because the most complex model in the spatial context is actually really complicated to estimate. It's really difficult to estimate. So sometimes impossible to estimate. I mean, it's really, that's why I discourage you from using discrete dependent variables in your empirical problem, because these models are really hard to estimate. So you just as soon not start with the most complex model and then cut back, but instead you move forward from the simple model, which is my preferred strategy, but there are major, major caveats, right? And the major, well, let me first do the sales pitch and tell you the good things, right? Good things is it's easy. You start with a simple model, you estimate it by means of ordinary least squares, you have the residuals, you use these Lagrange multiplier statistics to tell you what may be wrong with the model. Then let's say you find, they point you to an error model, you estimate the error model, and you do the whole diagnostic routine all over again, and so you keep going until you stop. And if you remember the very beginning, I mentioned there are two major effects in spatial modeling, spatial dependence and spatial heterogeneity. And one person's spatial heterogeneity is another person's spatial dependence. So you can think of it basically, if you wish, you start from a point, you go dependence or you go heterogeneity, and then you come back to putting the both of them together. But how you put them together, whether you do heterogeneity first and dependence later, or dependence first and heterogeneity later, typically both of these will be part of your model and have to be part of your modeling strategy. So that is a forward strategy. Let's say you find spatial dependence, you estimate a spatial model, you find heteroscedasticity, then you estimate a spatial model that incorporates some form of heteroscedasticity. That's the good part. The bad part is that your p-values are no good. So as I mentioned the other day, it's instantaneous amnesia, right? So there's no learning. Unlike Bayesian inference, which is all about learning, everything is conditional upon the previous step, so it all kind of hangs together. In classical statistic, there's a real awkwardness about this, right? So all these tests and their p-values, they're all fine in isolation. Where you get into trouble is when you chain them together. And a forward strategy is exactly that, right? A backward strategy is exactly that too. But let me get to that point in a second. But both of them, the moment you do more than one test, you suffer from the problem of pretesting and of multiple comparisons. So there's no real acceptable solution to this. There's lots of corrections and, tricks to deal with this, like Bonferroni bounds, which take a target p-value and divide it by the number of comparisons that you do, and other such things like that. Theoretically, you have a problem. In practice, well, maybe not so much. In practice, as you'll see in a lot of the examples that I show you, these p-values are off the chart. Sometimes they don't even print. It's all 0. So if you have all 0, and even think of that in a Bonferroni sense, if you do 5 tests, and you have 0.0000 and keep going, and divide that, or actually multiply that by 5 to have your operational p-value, that's still going to be 0 for all practical purposes, right? So in a lot of practical contexts, this is, I know I get in trouble for saying this is a non-issue. For practical purposes, it's a non-issue. Strictly speaking, and definitely theoretically, it's most certainly an issue, and it is something that classical statistics is very uncomfortable with. The whole process of statistical learning and multiple comparisons, that's one of the issues that's come to the fore even, in this new book by, I know one author is Bradley Efron. The other one, the name escapes me, but they're both at Stanford. So they have a new book about statistical inference for the modern age, or something along those lines, or for the computer age. It's really worth reading if you're into machine learning and statistical decision making, because it opens up some perspectives, and multiple comparison is one of these big boo-boos. How do you deal with that? Because everybody does it, but so what does that mean for your actual proper inference, right? So that's the bad part. So now let's look at the forward versus backward strategy. So forward strategy, you have an overspecified model. At worst, you have an issue of efficiency. So if you have a model with many variables that are irrelevant, it doesn't really affect the properties of the estimates of the other variables. It only makes them less efficient. Whereas, and we've already seen this, if you have an omitted variable problem, so you have a variable that should be in there, like our spatially lag-dependent variable, but we don't put it in there, then everything is off. Everything is wrong. Remember my little simulation where it starts moving outward. So that is the downside of the forward specification test. Because basically you're in this really uncomfortable situation where you start with a standard linear regression model. You use OLS to get your estimates. But your estimates, if the spatial lag model is the true model, then all these estimates are pretty bad. They're biased, they're inefficient, all that bad stuff. So then you're using these estimates to compute your residuals that you then use to decide whether the model should be a lag model or should be an error model. Think about that for a second. So it's fraught with difficulties, but then at the end of the day, that's the easiest way to go. But I do give you this context so that you don't do this mechanically. Think about it, because at every step of the way, there are some problems. There's the pre-testing problem. So if you are doing this and you end up in situations where you have to make decisions at the marginal, what I call on the bubble, right? Depending on your where you were trained as 0.05 or 0.01 or something arbitrary like that, right? So if you're working in that arena, don't go there, because you know that those p-values are not the correct p-values. But if you're in a situation where you have a bunch of zeros, I would say don't worry about it. I mean, yes, your p-value is not the one there, but it's not going to be 0.05 either, right? And so you know that you have something, even though it is imperfect. But that gets us very quickly on a slippery slope, right? The whole point of statistics and econometrics is to quantify uncertainty. And here we're saying, yes, we're quantifying it, but we know it's wrong. It's not too wrong. It's good enough. Once you get into that terrain, then the kind of house of cards starts to fall apart, and you have to be very careful. And that, to many, is the attractiveness of a Bayesian perspective, where you don't have that. You have other problems, but not that one. So, as I said, the backwards strategy is the other way around. We start from the most complicated model we can think of, and then we move backwards. And actually, in this paper that I cited at the beginning by former Florax and Ray, they did some simulation experiments, and it turned out at the end of the day, the forward strategy wasn't that bad at all. And so from a practical specification search perspective, as long as you keep the fine print in mind and all that stuff, you should be good. As you will probably run into in practice, it's not that simple, especially as the data sets get larger. And I mentioned this, I think I did last time, is that as the data sets get larger, there is more and more evidence, if you wish, that the null hypothesis is not maintained. So the power of these tests really increases, which means they're going to reject the null. And so then everything is going to reject the null. And they're going to reject the null against any number of alternatives. And then so then, in a sense, you're still at square one, because everything is highly significant, so which one is it, right? And so then we have to switch gears and go from a specification testing strategy to a model comparison strategy. And as we saw the other day, model comparison, forget R square. We can use the likelihood, which is not quite a fit, but it's a proxy. We can correct the likelihood, like these information criteria, or we can develop ad hoc measures like a pseudo R square or mean squared error or something like that, right? So what is the specification search, kind of the classic way, because I say so, is how does one proceed? And this is how really GeoDa was set up, and before that SpaceStat was set up. So forget about Moran's eye. You can kind of look at it with one eye, but you know, if nothing rejects the null and Moran's eye also doesn't reject the null, you're good. You're good to go, right? But if Moran's eye rejects the null, it could be anything. Literally. It's such a great misspecification test. It has such great power, right? But that doesn't really help you, right? So look at the LM tests. If they don't reject the null, you're done, right? Stay in the SPSS world. You don't have to go anywhere. If you have one or the other, then it's also very clear, right? So the LM error rejects the null, the LM lag model does not, LM lag test does not, then you go with the error model. And vice versa. If the LM lag rejects the null, but the error one doesn't, then you go with the lag model, and then you're done. If both reject the null, and only if, or I should say both reject the null, then you go to the robust test. And then it's the same thing. You use the same decision rule. If one rejects and the other doesn't, you're good. But unfortunately, increasingly with larger data sets, you may end up with both rejecting the null. So at that point, this whole strategy of the robust tests ceases to be useful, because basically a rule of thumb that I found in many, many simulation experiments is that whichever is the larger of the two points to the most relevant alternative, right? So it doesn't have, if they're both significant, you take the largest one. But if they're both significant, especially in larger, even 3,000 observations, then it's very difficult to tell the lag model from the error model. And then you may have to go back to the drawing board and rethink your model. Clearly, there is something going on, right? And at that point, as I mentioned before, the specification testing strategy ceases to be that useful, and then you have to go to a model comparison strategy. And you can compare models on fit or on other criteria, like the meaning, the interpretation of the coefficients, and so on. So as a rule, in that context, an error model is preferred over a lag model, because a lag model implies a substantive spatial interaction, and in many theoretical contexts, there isn't really a good reason to come up with a substantive interaction hypothesis. Of course, there are contexts where there is, the focus is on the interaction, and then, of course, a lag model is what you want to find. But typically, I mean, for example, economists would much rather have an error model than a lag model, because it's a mismatch between the scales, and all that stuff is all in the error term. It's a precision problem. It doesn't substantively change the model. We're good, right? If in a linear model. In nonlinear model, forget it. Nonlinear model, the errors are just as serious as the rest. But in a linear model, it's just a precision problem. You don't have to worry about it. The lag thing is a beast. A lot of people misinterpret it, and I told you I would say it a lot. It's typically misinterpreted in a conditional sense. The prices of my house depend on the prices of the neighbors. No, they do not. The pattern of the prices as a whole is determined by the pattern of the explanatory variables at the location as well as the neighboring locations. That is not your typical read of a spatial lag model. And that's why, you have to be really careful when you interpret those models and not fall into the conditional trap. So here's my flow chart. This has been around for years and has been abused as well as used. But that basically tells you what you do. So you go down, nothing rejects, done. One rejects, not the other. Run the other model, done, right? And then you can keep going, because actually, I didn't talk about this, but I think I did allude to it, but in the maximum likelihood framework, you can keep deriving these LM tests. So you can derive, and I've actually done this, an LM test for remaining error order correlation in a lag model. What you have to do for that is, of course, construct the likelihood function for the complex model and do all the derivation, and then set the constraints to 0. So that can all be done, but it's a monster. It requires large matrix manipulation, so it's not really very practical. So then if both reject, which unfortunately is the rule rather than the exception, then you move to the robust tests. And then again, same thing, one way or the other way. If they both reject, I hate to say, then you're in trouble. Right? Then you have to think of another way of dealing with this. Either refine your models, think about your weight structures, think about maybe nonlinear specifications, and if all else fails, you estimate both of them and you compare them in terms of model fit and model interpretation. That's why I like you to do simulations, because if you do simulations, you don't run into these problems. You have everything under control. If you do your empirical examples, first of all, there's always going to be one or two people who do not have any spatial effects in their data sets. I'm sorry, but it happens, right? And then I would say maybe a third will be stuck at the end of the line where both tests, robust tests, strongly reject the alternative, and there isn't really a good way to tell one model from another. You know, so, why, you've been there already? Yeah. See? I'm not making this up. I've been teaching this for years. You know, I've seen, I wouldn't say I've seen it all, but I've seen just about all. Okay, so here are my stylized, concocted examples where I painstakingly found a model with one of the sample data sets that I used to show you an example of these cases. So this was actually a challenge I had to my students at one point, because so you have to put things into context. When I worked on these things, it was in the late 70s and early 80s. And so the Spatial Econometrics book was published in 88. And the example I used, this Columbus 49 neighborhoods in Columbus example, the map was drawn by hand by the departmental cartographer. You know, so, you know, the weights were computed by eye, by just looking at the map and just coding what was the neighbor. So none of this GeoDa stuff where you just click and it gets done for you. So I was so happy that even though, you know, this data set, it's crime rates, so they're not typically not normally distributed, but all this stuff kind of worked. And so it was a great data set to illustrate all these different estimators and different cases, because it worked, okay? Only a number of years later, and you know, I know this data set with my eyes closed. So I ran this, I was trying to illustrate spatial heterogeneity, and I discovered there was actually a very simple specification that wiped out any evidence of spatial autocorrelation in that data set, right? And this is the model. So the model I used in the book and many times afterwards to illustrate different tests and estimation methods has the crime rate for each neighborhood regressed on the per capita income and the median housing values, right? And then I threw in an indicator, a dummy variable, an indicator variable, core periphery. And actually, now, you see, you have to put things into perspective. In those days, you didn't make maps. Making maps was something the cartographer did for you, and it took a couple of weeks, right? Now you just do them one after the other, and you can look at different visualizations. And in fact, as we started to make these maps, you could see it. It's just screaming at you. I mean, of course, you need to quantify this, but in the core of Columbus, there's a lot of crime. Outside, there isn't, right? So if you run this model, and it's a decent model, it has an R-square of basically 0.67, which is not bad. Everything is strongly significant to weakly significant for the housing value. So even though this is a concocted model, it's not that bad. The core periphery is very highly significant and, you know, high value as well. So here we do the tests. So nothing is significant. If anybody has run any analyses yet and you get this, talk to me, because, you know, I can get you spatial autocorrelation if you want it. This is not a recommended strategy, but sometimes it comes in handy, right? So here we have an illustration of the power of Moran's eye, because Moran's eye is picking up problems, whereas none of the spatial statistics do. And there is, in fact, some indication of heteroskedasticity, as you might expect. Right? So this is kind of the case you dream for if you're doing substantive work, but the case you dread if you're trying to do an assignment in a spatial econometrics class. Because now, what are you going to do, right? And the key, if you, and some of you may be in this situation, think spatial heterogeneity. Okay, that's still relevant. Okay, then I had to work a little bit on this to find one where there's clear evidence of just one type and not the other type. So in this case, we have a spatial error indication. You see what I'm doing, and this is, if you ever have to teach this, you might want to remember this. You change the weights, stick in a different variable, and all of a sudden, boom, we have still a reasonable model. It's in the mid to high 60%. Everything more or less significant. Again, housing values not so much. And here we go. So the Moran's eye, highly significant, right? LM lag, nothing. LM error, well, with a little bit of liberal interpretation, yes, right? So here the suggestion would be it's an error model. And the reason why I say, you know, even though it's literally 0.06, you might still want to estimate the alternative model is because remember the ranking, right? Asymptotically, the WALT, which is your t-test, and the Lagrange likelihood ratio test and Lagrange multiplier test are ordered like that. Asymptotically, they're the same. In finite samples, they're ordered. So the LM test is always the smallest one. So it could be, like here, that the LM test gets a p-value of 0.06, but your asymptotic t-test, because it's a larger value, might be at 0.02. So then, you know, you're going to have to think about what you do with that. But in practice, it is a safer strategy to not be too strict with these LM tests, because they are, I always get in trouble knowing which word to use, but I would say more conservative, but you might also say more liberal. The bottom line is their p-values will be larger than the p-values of your asymptotic t-test. So if you get 0.06, you're likely to get something more significant in an asymptotic t-test. And so there is something going on there, in other words, right? So then you might wonder, why is Moran's eye so significant? And then we look at the other things, and there's a high degree of heteroskedasticity and even non-normality in the Jacques-Perrat test. So that is what it's picking up, likely. In fact, I've done simulation studies that show, and I say this a lot, but Moran's eye is really a great misspecification test. You know, it picks up all kinds of stuff. Just like Durbin-Watson, actually, is also a great misspecification test. Okay, this is the reverse. Again, I changed the specification a little bit, and now we have spatial lag. So this is, again, Moran's eye is somewhat significant, spatial lag very strong, spatial error nothing, right? And just to illustrate my earlier point, there's no indication whatsoever of error, but the SARMA, the bottom one with the 2 degrees of freedom, is highly significant. So if you just look at that with your blinders on, you would say, I need a model with both a lag term and an error process, spatial process. But actually, you don't. You just need to deal with the lag, and the rest you don't need to worry about. So then we get to the next stage, which is fairly common, is that both LM tests reject to null, and then one of the robust forms, which after you filter out, they all drop in value, but one of the robust forms gives you a clear indication of where to go next. And you see I keep changing the model a little bit, and I change the weights as well. Again, these are all pretty decent models. So here, what am I saying here? No, this is not what I'm saying. Sorry, I wasn't reading my slide. What am I saying? Yeah. This is what I'm saying. Ignore. This is the case, and you do run into this. And, you know, we have regularly people on the listserv asking us, what do I do? You know, the robust test is significant, so this has got to be better, right? Then the regular one is not significant. Well, it's the other way around. If these are not significant, ignore the robust one, right? And you see there's Moran's eye again picking all kinds of stuff up. And this is what I meant. Both of them are significant, but one of the robust ones is, only one of the robust ones is significant. So the previous example was an example where you would not estimate any spatial model. In fact, any spatial dependent model, it's likely that the Moran's eye picks up some spatial heterogeneity of some form. So I'm switching models. So here, this is what I wanted to show you. So the lag test, off the charts. Error test, off the charts, right? And then it drops. This is the example from the slides in the class. This one drops to 2.4. This one drops to 5.5. So only this one is significant. And typically, but not always, if you actually estimate these models, you will find that the lag coefficient is not significant in a lag model, but the error coefficient is. But again, I have to put this into perspective because I just mentioned that these p-values for the LM test tend to be worse than for the asymptotic t-test. So it could be that, you know, your LM test of 0.11 actually has an asymptotic t-test that still is significant, right? But then at that stage, you use the model comparison, and if you do a likelihood ratio test, for example, you will almost always follow this rule. So these rules are kind of, I wouldn't say ad hoc, but they are based on a lot of simulation evidence, and they work. But that doesn't mean necessarily that the other model will be totally insignificant. It will not be as strong as the model that you point to in this, with this path. So then this one is the other way around. So again, you see how they drop from 115 to 20, from 95 to 2. So in this case, it's the other way around, and the robust lag remains significant. So that's the path where you want to be. And then I didn't want to show you one where you don't have any clear evidence. So let me just show you real quickly how this runs in GeoDa and GeoDa space. You probably have already done this. It's very simple. We've actually already seen this. So you'll have to load the weights matrix. That's the only complicated part. And if you have a project file, which I do have, but I've been doing so many different things that I don't actually trust it. So now we have a weights file in here. Regression. Let's take homicide rate 90. Resource deprivation, population, unemployment, divorce, MA. Specify the weights, very important. If you don't specify the weights, you can't run the diagnostics, and then you run them and they look exactly like the kind of slides that we have. So what do we have here? Here we have a situation that I said happens. So we have the lag test is significant, the error test is significant. So then we move to the robust forms, and both of them are significant. So what do you do now? Well, if you follow the rule of thumb, and this is supported by a lot of different simulation evidence, if you go with a lag model, it will be the model that fits the data the best. But you know, what you really should do is estimate both of them and then look at the relative fit. And I think we did this last time. I don't remember, but we can do it very quickly here. We run it, the lag model, and it's, so here's our log likelihood, 9382. We run the error model, and we have 9313. Let's see. $93.10. So 10 is a little higher than 13. The lag model fits the data a little bit better, okay? But this is where you really have to think about it, right? So are we going, I mean, this is a spatial regression class, so, you know, we have to pay attention to it. But if you're really trying to understand what is going on in your data, this is really almost too close for comfort, right? I mean, there's just, I mean, these likelihood statistics are basically the same, right? So then you have to start thinking, do I, you know, which of these models is really more meaningful in terms of what I'm doing? If you look at the pseudo R-square, actually, so it's basically the same, 0.454, and here is 0.452. So the squared pseudo R-square would argue in favor of the other way around, in favor of the error model. Now, why would that be? If you remember, how do we compute the pseudo R-square for the lag model? It's based on the prediction from the reduced form, which is a lot harder to do than the prediction in the standard regression model. The standard regression model, you know, on average, the error term washes out, so you don't have to worry about the contribution of the error term. Whereas in a lag model, you really have to get rid of this endogenous spatially lag-dependent variable, move it over, take the inverse to get the predicted values from the reduced form, and then we compute the pseudo R-square from that. So that tends to be a more conservative measure, but also in that sense a more, if I can use the word, robust measure. Because it really, I mean, you can cheat and compute the squared R-square by keeping the spatial lag-dependent variable on the right-hand side. And then it will be higher, but that's not really what you want. But as I said before, these R-squares are not really that comparable, so the best way to compare models in this context is to use the likelihood or the information criteria, which are going to be the same in this case. So then let me switch to GeoDa space, and it's going to be exactly the same thing. I just want to show you, and I may have showed you this already. So we go, and now we get the dbase file. And then here we have to load the weights file, which is our same queen file. And then we put the variables in the boxes. The reason I'm using GeoDa space is I'll show you the two-stage least squares case too. So we have the HR here, 90, right? Resource deprivation, 90. Then population, 90. Unemployment rate, divorce. Standard model, and it's the same thing. We have the exact same test down here. So that is all the same. Now let me show you the two-stage least square situation, which you cannot do in GeoDa yet. So unemployment rate, let's say that's endogenous. So instead of having it there, we move it over to the Y endogenous box. And you can have multiple endogenous variables in here. The spatially lag-dependent variable does not count. It's automatically dealt with as endogenous, so you don't have to specify that. But if you have another one, you need to specify it. And then, of course, you need instruments. And our instruments are here, the Gini coefficient, then female-headed households, and this one here. So you see the standard switches to GMM, which is really two-stage least squares. And we run this, and at the bottom here. So this would suggest a very high degree of spatial autocorrelation, but it doesn't tell you whether it's lag or error, because remember, it's a Moran's eye. It's not an LM error or an LM lag test, even though it looks a lot like an LM error test. It really isn't. It's a Moran's eye. So this just tells you, even with the endogeneity, there's a lot of problem in terms of spatial effects. So then we have to use not maximum likelihood, but the methods that we'll discuss next, which are based on either instrumental variables / generalized methods of moments, and do not assume normality, do not require a likelihood function, but do require very novel and sophisticated central limit theorems and laws of large numbers to get, at the end of the day, the same properties. So it's asymptotically normal, all that stuff, it's consistent, all those things, you get them from these specialized central limit theorems. So this is basically the setup of what I want you to do for your next deliverable. So at the second stage, you know, you have your data, you have your research question. Now you set it up as one or multiple, I mean, you do whatever you want, but at least one regression specification. And you run these diagnostics, look at the sensitivity to the weights that you use, so you have to run it more than once, and then deduce which would be the alternative model that is suggested by the data, right? And it could be that, you know, there's no clear evidence one or the other, but then really look at your weights and look at the sensitivity to the weights. You may find a specification that brings clarity in that. Because it's imperfect, right? These weights are ad hoc. They're based on contiguity, they're based on some kind of notion of potential neighbors, but if you underbound or overbound, you know, you don't really know that. That's the part in this analysis that makes theoretical people uncomfortable, because it is, unless you have a theory for the weights, it is, at the end of the day, basically an ad hoc procedure. Now, that's not a problem when it comes to specification testing, because you want power in your test. So whichever weights give you a test with good power is a good thing. But it does come back to bite you when you then estimate the model, because if you have a model with a crazy weights matrix, it's not going to be defensible, right? Okay.